Moving 1000 units around the map can be challenging, especially when you are making an RTS. I made this implementation using ECS for my RTS game that I'm currently working on. Let's first explore what is A star. A star is quite a popular pathfinding algorithm. It's very basic map of nodes, and you are giving a start and end point, and you go through this path. You basically what you give the algorithm is a start and end point, and this map of like walkable and unwalkable nodes, and then what you are given back is this path, the resulting path, which the entity would use to go through its movement system and move it along. In order to generate this path, you have three costs that you need to calculate. The G cost, which is how many nodes did you have to go through in order to get to this point, and the H cost, which is what is the distance, or the heuristic cost, which is what is the distance between this current node and the target node, and finally the F cost, which is the sum of the G and H. It's a very basic algorithm where you keep two lists. There is an open and closed list. You keep iterating over the neighboring nodes until you hit the target node, and by that time you have calculated all the possible F costs, and then you backtrack your way from the target node to the start node, and then reverse it and give it back to whatever entity needs it. So let's just take a look at how does that work. The good starting point for exploring this code would be the pathfinding job system. So um, I had to work out what is the best way to have this implementation multi-threaded as to support ECS, and just going through the code and how it works. We have this job system that requires specific components to exist, which are the pathfinding grid component, which is basically the grid by definition, and then the request component, which is you need to have at least one request component in order for the system to actually run and like add jobs. And then there is a pathfinding settings component, which is basically just some configuration component that you can use. For my game, I use the terrain authoring to set up those. So here you can see the pathfinding grid component and the settings component, and I do add the grid path node buffer, which is basically the node map, like the default node map that the global grid would use. And yeah, essentially we need to get the entity component buffer because every job will need to remove the request component. We need to use this singleton, which is basically creating a command buffer so that we can use it within the job that we created. Um, Other configuration stuff are there is this get singleton entity, basically getting the grid, and I get it as a dynamic buffer, which it can be a blob, but I thought maybe I need a buffer, so it doesn't really matter much for me, at least at the moment. I do reinterpret it as a native array, and then give it some configurations from the grid component, which is coming from the terrain authoring. Yeah, basically I give all these data to the job constructor, since it's something that will be always used, and then I just schedule parallel. Um, I Just a very quick explanation of how jobs works in ECS. This job implements iJob entity, which means that it will go through every entity that have the required components. So in this case, it's the pathfinding request component and the dynamic buffer for the path buffer, which is what we will where we will throw our path later on. And yeah, it the job itself is very straightforward. It's a very like straightforward implementation of the pathfinding algorithm, which we let's just give it a quick look. Uh, you can validate the coordinates. So the initial like validation steps are here, which is basically just making sure that the position is valid, that the start and end index are in the same, and both are actually walkable, as in like you can actually go there. And then there is this structures that I use. Some people would prefer having the path node itself have these data, but I just thought it's fine to use it as a native hash map. And then there's also the came from native hash map. And there is the open list, which is a native heap, which is a custom implementation I will show later. And there is a closed list, which is also a native hash map. Um, Essentially, what this does is just adding the first index to the open list, which is could also be named a priority queue. And basically, it just keeps on checking while there is something in this queue. Pop it, check if the current index is equal to the end index. If it's yes, then just mark it as found and like break from this while. Else, just keep on iterating and going through it. Eventually, the main point of interest here is that there is this current position and the current G cost, which is coming from this hash, which is basically just the G cost, which is like the how much it take, as I said, the to get to this point. And since it's the initial index, it's set to 0. And I just keep looking at the neighbors. So there are two for loops for the 8 directions. One is changing on the Y and one is changing on the X. If N and X are 0, just skip it. Otherwise, we continue with validation checks and then check the neighbor if the neighbor is walkable. And basically, we make sure that the neighbor is walkable, like this specific index here, and then uh, the closed list. We also check the closed list doesn't contain the neighbor, because if it does, then it's already like explored. No need to add it to like evaluate. I also do this corner checking for the diagonal, which is really relevant to this specific A star algorithm. But yeah, it just adds more data to serve on whether it's like if it's diagonal. If diagonal is enabled, you need to consider this. If diagonal isn't enabled, you don't need to consider this. But what it does is essentially just making sure that for diagonals it's also walkable. um, the next step is just making sure that the move calculating the move cost, which is essentially our heuristic cost. And um, this cost, we set it to 1 by the default, and then there is this diagonal modifier, which is basically square root of 2. And yeah, we just keep going. It check if there is a if the this G, which is basically the current G cost, which is how much did it take to be here plus whatever the move cost, because this is a neighbor. And then we check if the G cost exists and the tentative G, this new G cost is more than the existing one, then this is not a better pass, just ignore this. Otherwise, we update the G cost and we update the came from dictionary, which will come very helpful later on in this reconstruction part. Finally, we calculate the heuristic, we calculate the F cost, and then we just put it in the priority queue with the F cost and the heuristic cost, because that's how we use it for the node sorter, which is using the I comparable. If the F cost, just compare if the with the F cost, if the F cost is equal on both, we will need to a way to tie break, which is basically otherwise just use the heuristic cost. Um, yeah, that's it basically for our comparable. This is used by this men here within the native heap, because every time we insert something to the native heap, it gets like resorted to figure out what is the next, like what's the next best index to pop, which is the one with the lowest F cost. Um, yeah, essentially, after we get our pass through the algorithm, um, if we find something, we basically start reconstructing the path, and which is what this does. It just goes through the path indices. It starts with the end index and then goes with through the came from um, uh, dictionary or native hash map, and then it eventually just check for the buffer, keeps adding the indices from the global grid nodes, world position, and just eventually just dispose everything. Um, there are some helper methods, so let's take a look at that. So in order to calculate the heuristic, it's basically just a Manhattan uh, um, calculation. It does have the octile multiplier, which is the one that I was talking about with the square root of 2. That takes into consideration the diagonal like movement as part of the distance or the heuristic calculation. There is also the position valid and the calculate index and index to position, which is all just helper methods really for the job itself to work. That's essentially the main thing. Um, the other thing I wanna point out is the what type, how our components look. There is this path buffer, which is just carries out the position. It's used as part of the dynamic buffer so that you can actually communicate positions to go. And then there is this grid component, which is basically just setup for the grid. And there is a request component, which is basically a way to um, uh, communicate your need, and then like the system would eventually just communicate with the pass buffer in the entity that sent it, or like that had this component. It does remove this component after it's done. And I think that's it. Let's take a look at the obstacle system. So up to this point, we have a map fully with walkable nodes, and in this case, we gonna need to specifically specify where our obstacles exist. In my game, I put it somewhere around as part of the building placement algorithm or the building placement system. Let's see where that exists. It's in somewhere around here. So the build placement system, it should be somewhere around this area as far as I remember. Yep, there we go. So basically I just use the bounds, which is something I have when I place the preview. So there is some calculation that I use for the preview, and then I use this bounds to put down a size, bound size, and center offset. It does use that in this obstacle system, so this requires, of course, a grid component to exist, and then there is this job. I do reset the job, which is basically goes through everything and just resets it. And then the next step would be apply obstacles job, which is just go through every node and check if there is an obstacle at its place. This happens by like using the grid component and the transform. So let's say the entity of course has to have a transform. It uses a center offset and the bound size along with the transform position to just get the minimum x and minimum y, and then just iterates over it and mark it as not walkable. And that is it, I think. That's it, yeah. Um, Enjoy. I will share it on GitHub, so enjoy taking a further look into it. I did introduce an obstacle authoring baker just in case you wanna fiddle with it as part of this folder. I will see if I can make a demo using it. But yeah, that's it for me today. Thank you.